Galaxies are supposed to shine for billions of years, yet astronomers have found cosmic giants that went dark far too soon. This is the profound mystery of early quenched galaxies, a discovery that threatens to rewrite the story of our universe. By the end of this exploration, you will understand the leading theories for this cosmic extinction event and what it reveals about the fate of all galaxies, including our own. Why did these stellar cities stop building stars when the cosmos was still young? And what powerful force could silence them so completely? What does it mean for a galaxy to die before its time? To understand the scale of this mystery, we first need to grasp the story we thought we knew. The universe, in its grand design, follows a rhythm. After the initial chaos of the Big Bang, gravity began to pull matter together, forming the first stars and then the first galaxies. These early galaxies were cosmic construction sites, vast reservoirs of pristine hydrogen and helium gas. They were engines of creation, forging new stars at a furious pace, lighting up the darkness of the young cosmos. In this established timeline, the largest galaxies were the most active. They had the most raw material, the strongest gravitational pull to gather more gas, and they were expected to be the last to run out of fuel. The process of quenching, where a galaxy stops forming new stars, was seen as a slow, inevitable sunset. It would happen gradually over billions of years, as a galaxy either used up its gas reserves or as internal processes, like supernova explosions, began to blow the remaining fuel away. This was the natural life cycle, a long, productive adulthood followed by a slow, graceful fading. The universe had all the time in the world, so when astronomers pointed their telescopes back to when the cosmos was only a few billion years old, they expected to see these giant galaxies in their prime, blazing with the light of countless newborn stars. They did not expect to find cosmic ghosts. But the universe, it seems, loves a good plot twist. The Hubble Space Telescope, peering into the deepest reaches of space and time, began to find something unsettling. It spotted galaxies that were massive, yes, but they were not the brilliant blue-white nurseries of star birth. They were red. And in astronomy, a red galaxy is a quiet galaxy. Its color indicates a population of old, cool stars, with no hot, young, blue stars to balance the spectrum. These were not just slowing down, they appeared to be finished. The real shock came when astronomers measured their distance, calculating just how long after the Big Bang we were seeing them. The answer was staggering. Some of these red and dead giants existed when the universe was a mere 2 to 3 billion years old. To put that in perspective, our own Milky Way is over 13 billion years old and is still forming stars today. These galaxies had lived fast and died young, completing their entire star-forming journey in a cosmic blink. This was the core timing problem, a fundamental clash between prediction and observation. How could a galaxy so massive, with so much gravitational pull to attract fresh gas, run out of fuel so unbelievably quickly? It was like finding the ruins of a great civilization in what was supposed to be a vast, untouched wilderness. The James Webb Space Telescope, with its infrared eyes, has only deepened the mystery. It has confirmed that these early quenched galaxies are not rare flukes. They are a significant part of the early cosmic population. The universe, in its youth, was already hosting ancient relics. This discovery forces a single, unavoidable question. What catastrophic event, or what incredibly efficient process, could shut down star formation across an entire galaxy, not in a slow fade, but in what amounts to a cosmic instant? The color red in the night sky is a cosmic warning light. It signals that something fundamental has changed within a galaxy. Astronomers call this process quenching, and it is the definitive end of a galaxy's era of creation. But not all quenching is the same. Understanding the different ways a galaxy can be quenched is the key to unlocking what happened to those ancient, silent giants. Think of a galaxy as a vast, cosmic kitchen. To keep making new stars, it needs a steady supply of fresh ingredients, which is cold hydrogen gas. Quenching, then, is simply the process of cutting off the gas supply. But how you cut it off leads to two very different stories. The first is a slow, gradual shutdown, often called strangulation. In this scenario, the galaxy continues to cook with whatever gas it has left in its pantry, but no new deliveries arrive from the outside. Star formation continues for a while, using up the remaining reserves, but it slowly sputters out as the last of the fuel is consumed. The galaxy's color shifts from blue to red over billions of years, a long, lingering sunset. This is the peaceful, expected end we once thought was the rule. The second pathway is something far more dramatic. This is rapid quenching, a violent and sudden intervention. Here, something doesn't just stop the gas deliveries, it violently empties the kitchen. An immense burst of energy, often from the galaxy's own supermassive black hole, can blast the remaining cold gas out into the void, or heat it up so intensely that it can no longer collapse to form stars. The result is not a slow fade, but an abrupt, definitive silence. The transition from a star-forming galaxy to a red and dead one happens on a timescale that is astronomically brief, perhaps just a few 100 million years. Identifying which of these pathways a galaxy took is absolutely crucial to solving our mystery. If the early, massive galaxies were strangled, it implies their surrounding environment was somehow stripped of fresh gas incredibly early in cosmic history, a puzzle in itself. But if they were rapidly quenched, it points to a specific, catastrophic event internal to the galaxy. It means these young giants possessed or encountered a force of unimaginable power, a cosmic off-switch that could halt creation in its tracks. The red color of those distant galaxies is our only clue, a silent testament to a forgotten cataclysm. To read that clue, we must look for the culprit capable of such a decisive act. That cosmic off-switch may reside at the very heart of a galaxy. In the center of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole. These are not the destructive monsters of science fiction, but they are titans of gravity, with masses millions or even billions of times that of our Sun. For most of a galaxy's life, this central black hole is quiet, dormant, simply resting in the dark. But when it wakes up, it becomes the most powerful engine in the known universe. We call this an active galactic nucleus, or AN. As vast amounts of gas and dust spiral inward toward the black hole's event horizon, they don't just vanish. The material forms a swirling, superheated disk, a maelstrom of matter so energetic it glows across the entire electromagnetic spectrum. This process can unleash more energy than all the stars in the galaxy combined. And that energy does not stay neatly contained. It floods out into the galaxy in two primary ways. The first is through intense radiation, a blazing light that can heat the surrounding gas. The second, and more dramatic, is through colossal jets of charged particles. These jets can blast out from the poles of the black hole at nearly the speed of light, stretching for thousands of light years into intergalactic space. This entire phenomenon, where the black hole pours energy back into its home galaxy, is known as AGN feedback. And feedback is the key word here. It's not just an explosion, it's a regulatory mechanism. Think of it like a cosmic thermostat. When star formation runs too hot and too fast, producing huge amounts of gas and feeding the central black hole, the AGN switches on. Its outpouring of energy then heats up the galaxy's remaining reservoir of cold gas. This is the crucial detail. To form new stars, gas must be cold and dense enough for gravity to pull it together into collapsing clouds. By superheating this gas, the AGN prevents it from cooling down and condensing. It keeps the fuel in a state where it's too energetic, too turbulent, to ever settle into a stellar nursery. In more extreme cases, the jets can physically push the gas out of the galaxy entirely, stripping it away into the void. The result is a rapid and comprehensive shutdown. Star formation doesn't just slow, it stops. The galaxy, having silenced its own engine of creation, begins its transition to the red and dead state we observe. This makes AGN feedback a prime suspect for our early quenched galaxies. A massive, voracious black hole at the center of a young, gas-rich galaxy could, in theory, activate and quench its host in a relatively short cosmic timeframe. It provides a powerful, internal explanation for a sudden, galaxy-wide extinction event. But a good suspect needs more than just motive and opportunity. It needs evidence placed at the scene of the crime. Can we find proof that these ancient, silent giants were once ruled by such furious hearts? But a supermassive black hole is not the only titan capable of such cosmic violence. There is another event, equally dramatic, that can reshape a galaxy's destiny in a single, catastrophic encounter. This is the galactic merger, when two entire star cities are drawn together by gravity in a slow, inevitable dance that ends in a spectacular collision. For billions of years, these galaxies may orbit each other, their mutual pull stretching out vast streams of stars and gas in long, luminous tidal tails. It is a beautiful and destructive process, and within that chaos lies a paradoxical truth. A merger can be both the greatest catalyst for star birth and the reason that star birth ultimately ceases. This is the theory of Blitz quenching. When two gas-rich galaxies finally merge, their combined reservoirs of cold hydrogen are violently stirred together. This creates immense shock waves and pressure waves that ripple through the gas, triggering a frenzy of gravitational collapse. The result is a starburst, a furious, galaxy-wide firestorm of star formation that can outshine the combined light of both original galaxies. For a short, brilliant period, the merger remnant becomes one of the brightest objects in the universe, birthing stars at a rate hundreds or even thousands of times faster than our Milky Way does today. But such a fire burns hot and fast. It consumes the available fuel with staggering speed. Think of it like pouring an entire can of gasoline onto a campfire all at once. You get a spectacular, roaring blaze, but it is over in moments, leaving only ash and embers. In a galactic blitz, the starburst rapidly consumes the very cold gas needed to sustain it. Furthermore, the incredible energy released by all those newborn stars, with their powerful stellar winds and eventual supernova explosions, can heat up or blow away any remaining gas that hasn't already been used. The merger itself also disrupts the orderly structure of the galaxies, potentially funneling vast amounts of gas directly into the central supermassive black hole, igniting a powerful episode of AGN feedback that delivers the final, quenching blow. The outcome is a galaxy that has lived its entire star-forming life in a single, glorious and brief crescendo. After the storm passes, it is left with a population of aging stars and little to no fuel for a second act. It becomes red, quiet, and massive, exactly the type of object we see in the early universe. This blitz scenario offers a compelling explanation for why some galaxies died so young. They did not fade away quietly. They went out in a blaze of glory, their final, furious burst of creation sealing their own fate. The evidence for this can be seen across the cosmos in the distorted, merging galaxies captured by our telescopes, each one a possible snapshot of a future red and dead giant in the making. Yet a galaxy does not live in isolation. It exists within a vast cosmic web, a network of filaments and clusters where gravity gathers thousands of galaxies into dense, swirling metropolises. To enter such a place is to step into a different set of physical laws, an environment so extreme it can rob a galaxy of its very essence. This is the third major suspect in our cosmic mystery, the role of environment. Within a massive galaxy cluster, the space between galaxies is not empty. It is filled with a searing, thin soup of superheated gas known as the intracluster medium. This gas is so hot it glows in X-rays, and it represents the accumulated atmosphere of the entire cluster, a relic of billions of years of galactic evolution. For a galaxy falling into such a cluster for the first time, this environment presents a profound hazard. As the galaxy plunges through this thin but scorching plasma at incredible speeds, it experiences a cosmic headwind of unimaginable force. Astronomers call this process RAM pressure stripping. Picture a galaxy as a car driving through a torrential downpour. The rain is the intracluster medium. If the car is moving slowly, the rain mostly hits the windshield. But if the car is racing at high speed, the rain hits with such force that it can peel the paint right off. In a galactic context, that paint is the galaxy's own reservoir of cold hydrogen gas, the very fuel for future stars. The immense pressure of the onrushing cluster gas can literally blow this cold gas out of the galaxy, stripping it away into the swirling intracluster medium. The result is a galaxy that has been environmentally quenched. It enters the cluster rich with potential and leaves it gas-poor and silent, its star-forming future stolen by the sheer violence of its surroundings. We see this process in action in nearby clusters like Virgo, where galaxies often appear with long, ghostly tails of gas being pulled away, clear evidence of this cosmic robbery. The mechanism is powerful, proven, and efficient. But for it to be the culprit behind the early quenched galaxies, it faces a significant timing problem. Galaxy clusters themselves take time to assemble. The immense gravitational wells needed to create that searing intracluster medium and the crowded conditions for high-speed collisions are products of a more mature universe. Could these dense environments have formed and become this destructive when the cosmos was only 2 or 3 billion years old? Recent observations from telescopes like James Webb are beginning to suggest the answer might be yes. They are finding hints of proto-clusters, the dense seedlings of future giant clusters, existing astonishingly early. If a massive galaxy wandered into one of these primordial, chaotic environments, it could have faced a version of ram pressure stripping even more intense than we see today. The conditions would have been raw and violent, potentially capable of quenching a galaxy in a rapid, dramatic fashion. So environment remains a compelling suspect, a reminder that a galaxy's fate is not written solely by what is inside it, but by the dangerous neighborhood it chooses or is forced to inhabit. With 3 powerful suspects now on the table, each with motive and some circumstantial evidence, the mystery only deepens. Could a single one of these forces be responsible, or is the truth a far more complex collaboration? The violence of a black hole or a galactic merger paints a dramatic picture. But what if the truth is quieter, more subtle, and written into the very architecture of the galaxy itself? Beyond the cataclysmic events, there exists an internal, structural pathway to silence, a process astronomers call morphological quenching. This theory suggests that a galaxy's own shape and stability can become the reason it stops creating stars. To understand this, think of star formation as a delicate dance. It requires cold, dense clouds of gas to become unstable, to fragment and collapse under their own gravity. That instability is the seed of a new star. But what if the galaxy's structure acts to prevent that instability from ever taking hold? Imagine a massive, swirling disk of stars and gas, like our Milky Way. For stars to form, pockets of gas within that disk need to be jostled, compressed, and nudged together. This often happens through gravitational interactions, spiral density waves, or collisions between gas clouds. These are the disturbances that trigger the collapse. Now, envision a galaxy that develops an incredibly massive central bulge. This bulge is a dense, spherical swarm of stars at the galaxy's heart. Its immense gravitational presence changes everything. It stabilizes the entire rotating disk of gas around it. The strong, orderly gravitational field from this central bulge suppresses the random motions and density fluctuations within the gas disk. It smooths everything out. The gas becomes too stable, too settled, to easily fragment. It's like trying to form ripples and waves on the surface of a pond that has been covered with a thick, rigid sheet of ice. The potential for disturbance is still there, but the structure prevents the chaotic motion needed to begin the process. The gas remains present, it is not blown away or heated to extremes, but it is effectively locked in place, unable to take the final step to collapse into new stars. This internal quenching is a gradual, structural shutdown. It does not require a monstrous black hole outburst or a catastrophic merger. It is a natural consequence of a galaxy maturing into a certain, very stable architectural form. A massive, red and dead galaxy with a prominent bulge could simply be a cosmic entity that organized itself into a state of perfect, silent equilibrium. Its star-forming days ended not by a bang, but by the profound stillness of its own design. This introduces a fascinating possibility that a galaxy's fate may be sealed not by the disasters it encounters, but by the serene structure it builds. The suspects line up, each with a compelling story. But a breakthrough in recent years has handed a critical piece of evidence to one theory in particular. Astronomers, using the combined power of telescopes like Hubble and the Chandra X-ray Observatory, have begun to measure the masses of the supermassive black holes at the hearts of these ancient, silent galaxies. What they found was not just surprising, it was a direct challenge to our understanding of how galaxies and their black holes grow together. In many of these early quenched giants, the central black holes are not just massive, they are what scientists call overmassive. This means they are far larger than they should be for the size of the galaxy they inhabit. In the local, modern universe, there is a tight correlation between the mass of a galaxy's central bulge and the mass of its supermassive black hole. They seem to grow in lockstep, as if one regulates the other. But in the early universe, this relationship appears broken. These black holes are cosmic heavyweights living in galactic bodies that, by comparison, seem too small. This is a vital clue. If the black hole grew to such a tremendous size first, it implies a period of incredible runaway consumption. It gorged on the surrounding gas, becoming a dominant force within its galaxy long before the galaxy itself had finished assembling its full complement of stars. This sequence of events is exactly what the AGN feedback theory needs. A black hole that becomes overmassive is a black hole that has been exceptionally active. Its period of furious growth would have been accompanied by a tremendous outpouring of energy, the very feedback needed to heat and expel the galaxy's remaining gas. The quenching, therefore, would not be a random catastrophe, but the direct and inevitable consequence of the black hole's own explosive adolescence. The galaxy, in a sense, is silenced by the premature maturity of its own heart. This evidence transforms the AGN from a mere suspect into a prime mover. It suggests that in at least a significant population of these early quenched galaxies, the story begins not with a merger or a harsh environment, but with a central engine that grew too powerful, too fast. It consumed its future in a blaze of self-destructive glory, leaving behind a massive, dark anchor in a sea of aging stars. Yet a single clue, no matter how compelling, does not close a case. The universe is rarely so simple. Could these overmassive black holes themselves be the product of an even earlier, more violent event? Every star begins with a simple, cold ingredient. Deep within the swirling clouds of a galaxy, pockets of molecular hydrogen gas must chill to near absolute zero, becoming dense and still enough for gravity to pull them into collapsing spheres. Without this cold, quiet gas, a galaxy cannot create new stars. It is the fundamental fuel of cosmic construction. So when astronomers finally managed to peer into the hearts of those ancient red giants, they were looking for one thing: the telltale signature of this cold molecular hydrogen. What they found, or rather what they did not find, presented the mystery in its starkest form. These galaxies were not just quiet, they were empty. Their reservoirs of cold star-forming gas were almost completely depleted. This discovery moved the investigation from theorizing about causes to confronting a direct, physical reality. The fuel was gone. This absence poses the central, tangible question of the entire case. How did these massive galaxies lose their foundational resource so completely and so early? The answer must lie in one of three stark possibilities. Perhaps these galaxies never managed to acquire a large reservoir of cold gas in the first place. An odd failure for something so massive. Maybe they acquired it and then burned through it with incredible, unsustainable speed. Or, most dramatically, they might have had it, and then had it ripped away by some immense external or internal force. Each path leads to a different culprit, and the evidence within the galaxies themselves holds the key. The first generation of stars may hold the key to this emptiness. In the pristine dawn of the universe, the raw materials for star formation were fundamentally different. There was only hydrogen and helium, the two lightest elements forged in the Big Bang. Everything heavier, the carbon, oxygen, iron, and silicon that make up planets and life itself, did not yet exist. They would be forged later, in the fiery hearts of those first stars and in their explosive deaths. This primordial composition created a unique and potent environment. Without heavier elements, the gas clouds could cool only through a very limited set of processes. This lack of efficient cooling might seem like it would hinder star formation, but astrophysicists suspect it had the opposite, dramatic effect. It may have led to the birth of stellar titans on a scale we never see today. In the absence of the complex chemistry that allows modern gas clouds to fragment into many small clumps, these primordial clouds may have collapsed directly into monstrously huge stars, hundreds of times the mass of our Sun. These first stars, known as population 3 stars, would have been cosmic behemoths, and with great mass comes a ferocious, brilliant, and tragically brief life. A star that massive burns its nuclear fuel at a staggering rate. It lives for only a few million years, a fleeting instant on the cosmic clock, before ending its life in a cataclysm so powerful it can briefly outshine an entire galaxy. This is a pair instability supernova, an explosion of such total annihilation that it leaves behind no remnant, no black hole or neutron star, just a spreading wave of newly forged heavy elements that pollute the surrounding gas. Now, consider a young, massive galaxy forming in this era. If its first wave of star formation was dominated by these colossal, short-lived titans, the consequences would be profound. The galaxy would experience a starburst of unimaginable intensity, lighting up the early cosmos with a furious blue glare. But this firestorm would consume the available primordial gas at a breakneck, unsustainable pace. The fuel would be converted into stars and then, almost immediately, blasted back out into space as enriched debris by the ensuing supernova. This process, known as self-quenching, presents a startling possibility. A galaxy could effectively strangle its own future in its very first act of creation. It would use up its pristine fuel supply so rapidly and so completely that there would be little left to form a second, more sustainable generation of smaller, longer-lived stars. The galaxy's stellar population would age in unison, all its stars born in that single, brief, and profligate burst. After a few 100 million years, as the massive blue stars died off, only the longer-lived, smaller, redder stars would remain. The galaxy would transition directly from a brilliant blue beacon to a quiet red relic, having skipped the long, steady era of star formation we see in galaxies like our Milky Way. This theory elegantly explains both the early quenching and the puzzling absence of cold gas. The galaxy didn't lose its fuel to an external villain or a central black hole. It simply spent it all in one extravagant, youthful spree, leaving itself with a magnificent but silent legacy. It is the cosmic equivalent of inheriting a vast fortune and spending it all in a single, glorious year, ensuring a quiet, if comfortable, rest of one's life. The question then becomes, can we find evidence of this ancient, extravagant spending spree in the light of those distant red galaxies? There is an invisible architecture shaping every galaxy's destiny. Beyond the stars we see, and the gas we can measure, lies a hidden scaffold of gravity, a vast sphere of dark matter that cradles the entire luminous city. This dark matter halo is the true gravitational anchor of a galaxy, the unseen hand that dictates its growth, its structure, and, according to a powerful theoretical framework, its ultimate fate. The connection between this invisible halo and the quenching of stars is one of the most elegant and influential ideas in modern cosmology. It suggests that a galaxy's life story is not written by chance, but by the weight of the dark matter that surrounds it. Think of it this way. The visible galaxy of stars and gas is like a brilliant chandelier hanging in a grand, unseen cathedral. The size and strength of that cathedral, the dark matter halo, determines everything about what the chandelier can become and how long it can shine. For a galaxy to keep forming stars, it needs a continuous supply of fresh, cold gas flowing in from the cosmic web. This inflow is governed by the halo's gravity. A moderately massive halo pulls in gas steadily, feeding the star-forming engine at a sustainable rate. But if a dark matter halo grows too massive too quickly, everything changes. When the halo's mass crosses a critical threshold, estimated to be around 100 trillion times the mass of our Sun, the physics of the gas within it undergoes a fundamental shift. The gas falling into such a deep, powerful gravitational well doesn't just gently settle. It gets compressed and heated to extreme temperatures as it plummets inward, reaching millions of degrees. At these temperatures, the gas becomes what astronomers call a hot halo. It glows faintly in X-rays, and, crucially, it cannot easily cool down and condense to form new stars. It's like trying to make snowflakes inside a blast furnace. The fuel is there, but it's in a state that is useless for the delicate work of star formation. This theoretical transition point is known as the halo-quenching mass. Once a galaxy's dark matter halo grows beyond this limit, the steady, cold inflow of gas is thought to shut off. Star formation may continue for a while using any remaining internal reserves, but the main supply line from the cosmos is severed. The galaxy is effectively cut off, destined to quench. This framework provides a beautifully simple, universal rule. The most massive halos should host the first galaxies to stop forming stars. And this is where the mystery of our early quenched galaxies finds a potential, overarching explanation. What if these ancient red giants were not just galaxies that formed early, but galaxies that formed within the first, exceptionally massive dark matter halos to cross that critical threshold in the young universe? They would have been the pioneers, the first to experience this cosmic rite of passage. Their immense invisible halos, assembled by chance in the densest knots of the early cosmic web, would have heated their gas supplies prematurely, stranding them in a state of luminous silence while the rest of the cosmos was still bustling with stellar birth. This idea shifts our perspective from hunting for a single catastrophic event to understanding a predetermined destiny. The galaxy's visible fate was sealed by the incredible, unseen mass of its dark matter cradle. It was born into a cathedral so grand, it could not help but grow quiet. But the central black hole is not the only source of power within a galaxy. Long before a supermassive heart awakens, the galaxy's own stars can shape its destiny. This is stellar feedback, a universal force that arises from the very act of creation. Every massive star, many times heavier than our Sun, is a tempest in its own right. It burns furiously hot, emitting intense ultraviolet radiation and generating powerful stellar winds that stream from its surface like a relentless cosmic gale. And at the end of its brief, brilliant life, it dies in a supernova explosion, an event that can briefly outshine its entire host galaxy. Each of these processes pours energy back into the surrounding gas. The radiation ionizes and heats it. The winds push and churn it. The supernova blasted outward in vast, expanding shockwaves. This is the galaxy's own internal weather system, a constant, churning turbulence driven by its youngest and most massive inhabitants. In a modern galaxy like the Milky Way, stellar feedback is a regulating force. It helps prevent gas from collapsing into stars too efficiently. It enriches the gas with heavy elements, and it can even carve out great bubbles and cavities in the interstellar medium. But it is rarely, on its own, powerful enough to completely empty a galaxy of its fuel. The gravity of the galaxy is typically strong enough to hold onto most of the gas, even after it's been stirred and heated. The question for our early universe mystery is whether this balance could have been catastrophically different. Could stellar feedback, in the unique conditions of the primordial cosmos, have been amplified into a quenching force of its own? The environment of an early galaxy was a perfect storm for such an outcome. The gas was pristine, lacking the heavy elements that help modern gas clouds cool efficiently and fragment into many small stars. This may have led to the formation of those first, monstrously massive population, 3 stars we discussed earlier. A galaxy dominated by such behemoths would experience stellar feedback on a scale we can barely comprehend. The radiation would be more intense, the winds more ferocious, and the supernova unimaginably powerful. Instead of a gentle regulatory breeze, the galaxy would be battered by a continuous hurricane of energy from its own stellar population. This relentless stellar onslaught could potentially heat the gas reservoir to the point where it could no longer cool and collapse, or even drive it out of the galaxy entirely in a vast, sweeping outflow. Think of it not as a single catastrophic explosion, but as a sustained, deafening roar from a million furious voices that slowly pushes everything of value out the doors. This scenario, where a galaxy's own star formation sows the seeds of its own silencing, is a powerful alternative to the black hole hypothesis. It requires no special trigger, no rare merger, no dense environment. It simply follows from the natural, if extreme, physics of the earliest stellar generations. The galaxy would blaze with incredible light for a few tens of millions of years, a beacon of furious creation, and then fall silent as the very engines of that creation scoured away the fuel for their successors. It is a story of self-inflicted quiet, where the first and only song a galaxy ever sings is so loud it shatters the instrument. Determining the exact moment a galaxy fell silent is perhaps the greatest challenge in this entire investigation. We see the red color, the absence of cold gas, the overmassive black hole. But these are all clues to a crime scene that is billions of years cold. To understand the when of quenching, astronomers must become cosmic detectives, using the light from these distant galaxies to piece together a timeline of their final days. The primary tool for this is a galaxy's spectrum, the detailed fingerprint of its light broken down into every individual color. Within that rainbow, the subtle signatures of different types of stars are imprinted. Young, massive, blue stars leave one kind of mark. Older, cooler, red stars leave another. By carefully analyzing the mix of these signatures, scientists can estimate the age of the galaxy's stellar population. They can ask, when was the last major burst of star formation that contributed a significant number of stars we still see today? This technique, called stellar population dating, is powerful, but it is not a precise clock. It provides a range, an epoch. Think of it like walking into a grand, silent ballroom after a party has ended. By looking at the state of the decorations, the half-empty glasses, and the tired faces of the few remaining guests, you can deduce that the main celebration probably ended a few hours ago. But you cannot pinpoint the exact minute the music stopped. The light we receive is a blended echo of every star that ever shone in that galaxy. The brilliant blue light from the last generation of massive stars fades quickly when those stars explode, leaving behind the more persistent glow of longer-lived, smaller, redder stars. This blending makes it incredibly difficult to distinguish between a galaxy that quenched very rapidly 500 million years ago, and one that had a slow, sputtering decline that ended 800 million years ago. That difference of 300 million years, an incomprehensible span to us, is a critical detail in the cosmic timeline. It is the difference between a sudden, violent event and a long, drawn-out process. Adding to the complexity is the phenomenon of cosmic redshift. Because the universe is expanding, light from distant galaxies is stretched to longer, redder wavelengths as it travels across the vast emptiness to reach us. This stretching is directly related to distance and time. The more redshifted the light, the farther away the galaxy, and the further back in time we are looking. Measuring the redshift gives us the galaxy's age, telling us when we are observing it, but it does not tell us when, within its own long life, the quenching occurred. We see a red and dead galaxy at a time when the universe was 3 billion years old. Did it quench when the universe was 2.5 billion years old, or just 200 million years before we observed it? Our tools struggle to see that fine a detail across such gulfs of time and space. This inherent uncertainty in dating the quenching epoch is not a flaw in the science. It is the fundamental nature of the mystery. It means that every theory, from AGN feedback to Blitz quenching, must account for a range of possible timelines. The when remains tantalizingly fuzzy, a blurred timestamp on a cosmic photograph, forcing us to rely on the other clues, the how and the why, to reconstruct the story of a silence that echoes across the ages. Among the silent giants of the early cosmos, one type stands out as the most extreme and puzzling. Astronomers call them red nuggets. The name itself is a clue, a compact, dense, and impossibly ancient stellar city. These are not the sprawling spiral galaxies we know today, with their vast, starry disks and graceful arms. A red nugget is a cosmic fossil, a relic of a different architectural era, and it represents the purest, most challenging form of the early quenching mystery. To find one is to look back to a time when the universe was perhaps only 3 billion years old, and to see a galaxy that appears not just quiet, but finished. Its light is overwhelmingly red, signaling an absence of young stars. Its shape is smooth and elliptical, lacking the structured disks of active star formers. But the most startling property is its size. Despite containing hundreds of billions of stars, a red nugget is incredibly small, often only a fraction of the diameter of our Milky Way. This means its stars are packed together with unimaginable density. Picture our entire galactic neighborhood, with its vast tracts of empty space between stars, crushed down into a sphere 1/10 the size. The stellar density at the core of a red nugget is thousands of times greater than it is around our Sun. This compactness is the first major clue to its history. It suggests these galaxies formed their stars in an incredibly intense, rapid, and early burst, building their entire stellar mass in a furious spasm of creation before the universe had even properly settled. Then, something stopped that process dead. For the rest of cosmic history, over 10 billion years, these galaxies have simply existed, their stars aging in unison, barely growing in size, becoming living snapshots of the universe's violent youth. They are not just quenched, they are preserved. The existence of red nuggets forces two staggering questions. How did a galaxy form so many stars so quickly and in such a confined space? And what mechanism could be so absolute, so efficient, that it not only halted further star formation, but also prevented the galaxy from expanding and evolving in size over the eons that followed? Every theory we have discussed faces its ultimate test with these objects. An AGN feedback event would have needed to be phenomenally powerful and precise, quenching the galaxy without disrupting its incredibly tight stellar structure. A merger-driven blitz would have had to be the final, defining merger, after which no further gas could ever be acquired. The dark matter halo scenario fits elegantly, as these galaxies likely reside in the most massive early halos, but it still must explain the profound compactness. Red nuggets are the archetypal early quenched galaxy. They are not a side note in the mystery, they are the mystery in its most concentrated form. Studying them is like finding a perfectly preserved seed from a prehistoric plant, a tiny, dense package that contains the blueprint for an entire lost era of cosmic growth. Their very existence tells us that the young universe operated under different rules, capable of building and then silencing entire galactic worlds with a speed and finality we are only beginning to comprehend. The early universe was not just a place of creation, but of fundamental transformation. Before the first stars flickered on, the cosmos was a vast, dark, and neutral sea. Hydrogen atoms, the most abundant substance in existence, drifted through the expanding darkness, their single protons and electrons bound together in perfect neutrality. This era is known as the Cosmic Dark Ages, but that darkness was not destined to last. As the first stars and galaxies ignited, they unleashed a flood of energetic ultraviolet light. This light did not simply illuminate the void, it began to tear the fabric of the universe itself at a subatomic level. Photon by photon, this radiation began to strip electrons away from the hydrogen atoms that filled all of space. This monumental process, which unfolded over hundreds of millions of years, is called the Epoch of Reionization. It marks the moment the universe became transparent, energetic, and fundamentally different. For a galaxy trying to form in this turbulent dawn, reionization was not a distant event. It was the very atmosphere in which it was born. And that atmosphere may have held a profound consequence for our mystery of the early quenched galaxies. The intense background radiation from this universal transition acted like a pervasive, cosmic heat lamp. For smaller galaxies, those forming within less massive dark matter halos, this was a potentially lethal environment. Their gravitational grip on their own gas was relatively weak. When the ultraviolet light from the first generations of stars and galaxies heated the hydrogen gas throughout the cosmos, it raised the baseline temperature of intergalactic space. For a small halo trying to pull in cool gas to fuel its growth, this was a devastating setback. The gas it needed was no longer cool and easy to capture. It was now warm and energetic, making it far more difficult for the modest gravity of a small halo to pull it in and condense it into stars. In essence, reionization may have raised the minimum size required for a galaxy to form successfully. It could have permanently stifled star formation in the smallest, earliest systems, effectively quenching them before they ever had a chance to truly thrive. But could this process, which targeted the smallest halos, also have impacted the massive galaxies that are the focus of our mystery? The connection may be indirect but crucial. A giant galaxy does not form in isolation. It grows by drawing in gas from its surroundings and, over time, by absorbing smaller satellite galaxies. If reionization suppressed or delayed the formation of these smaller building blocks, it could have altered the entire growth trajectory of the larger galaxy. The giant might have assembled its stars in a different, more rapid, and less sustainable way, using up its initial gas reserves in a single intense burst because the steady trickle of new material from smaller neighbors was cut off. The epoch of reionization, therefore, might not be the direct killer of massive galaxies, but it could have been the architect of the conditions that made them vulnerable. It set the stage, creating a universe where only the strongest gravitational wells could continue to gather cold gas, and where the rules of growth were written in the searing light of the first dawn. This universal baptism by fire may have predetermined which galaxies would flourish for eons, and which would shine brilliantly, briefly, and then fall silent forever. Theoretical models paint a vivid picture of cosmic history, but they are only as good as the rules we give them. Our most advanced supercomputer simulations, which attempt to recreate the entire evolution of the universe from its first moments, are now facing a stubborn and revealing problem. When they run the clock forward, these digital universes consistently fail to produce enough of those massive, red, and silent galaxies at such early times. The simulations show galaxies quenching, but not nearly as early nor in the great numbers that our telescopes actually observe. This is not a small error. It is a glaring mismatch between our best theoretical understanding and the hard evidence written in starlight. It tells us in no uncertain terms that something is missing from our equations. The physics we have programmed into these virtual cosmos is incomplete. Perhaps we have underestimated the sheer power of early AGN feedback, or the devastating efficiency of those first stellar generations. Maybe the properties of dark matter itself are subtly different than we assume, affecting how quickly those massive halos formed and heated their gas. This discrepancy is not a failure of science, it is a vital clue. It forces theorists back to the drawing board to invent new mechanisms or amplify existing ones, in an attempt to make their digital universes match the quiet, ancient giants we see. Every time a simulation falls short, it highlights a gap in our knowledge, pointing directly at the processes we do not yet fully understand. The silent galaxies of the early universe are not just astronomical objects. They are cosmic referees, judging our models and showing us exactly where the mysteries lie. Yet for all the power of a central black hole or the fury of internal starlight, a galaxy's survival depends on something far more humble, a steady supply of fuel. This leads us to a quieter, more systemic possibility for early quenching, one that focuses not on a violent event, but on a profound failure of supply. Imagine a galaxy not as an isolated island, but as a city connected to a vast, continent-spanning river system. This is the cosmic web, the grand scaffolding of the universe, a network of dark matter filaments along which streams of pristine, cold hydrogen gas flow like celestial rivers. For billions of years, this is how a healthy galaxy grows. It sits at the intersection of these filaments, drinking from these rivers of cold gas, converting the inflow into new generations of stars. It is a constant, nourishing drip feed that sustains the stellar population. But what if that drip feed was suddenly, permanently shut off? This is the theory of accretion quenching. It proposes that the earliest massive galaxies were not necessarily destroyed from within, but starved from without. Their connection to the cosmic web's lifeblood was severed. The most likely culprit for this severance is, once again, heat. As a dark matter halo grows incredibly massive, the gas falling into it from the web doesn't just flow in calmly. It plummets into such a deep gravitational well that it gains tremendous speed, crashing into itself and heating up to millions of degrees. This forms a hot halo, a vast, diffuse atmosphere of searing plasma that surrounds the entire galaxy. This hot halo presents an impassable barrier for any new, cold gas trying to flow in from the cosmic web. Think of it like a protective bubble of steam surrounding the galaxy. When fresh, cold river water, in the form of a filamentary stream, tries to penetrate this bubble, it doesn't stay cold for long. It is instantly vaporized by the intense heat, its atoms scattered and energized, becoming part of the hot halo itself. It never reaches the galactic core in a cool, dense state where it could collapse to form stars. The galaxy's primary supply line is effectively cut at the border. It still has gravity, it still pulls material in, but that material arrives in a useless, hot state. The galaxy is left to live on whatever cold gas it already has in its reserves, and when that is gone, the silence begins. This process provides a beautifully elegant and universal explanation. It doesn't require a specific catastrophe. It is simply a natural consequence of a galaxy growing too massive, too early. The first galaxies to cross that critical mass threshold would have been the first to cook their own incoming fuel, dooming themselves to a future of quiet maturity while the cosmos around them was still young and chaotic. Their greatness, their immense gravitational pull, became their own cage, insulating them from the very rivers that once fed their brilliance. This diversity of form and location is our final, and perhaps most important, clue. The early quenched galaxies are not a single, uniform class of cosmic relic. They are a varied population, each with its own story etched in starlight. Some are the dense red nuggets, compact and isolated, like ancient fortresses built on solitary hilltops. Others are more extended, their stars spread out in vast, lazy ellipses. And while some are found in the crowded cores of early galaxy clusters, others drift in the profound solitude of cosmic voids, far from any neighbors. This variation is not a minor detail, it is a profound revelation. It tells us that no single culprit can be responsible for this great cosmic silence. The early universe was not a place with one rule for how galaxies die, but a laboratory of extinction, experimenting with multiple pathways to quiet. A galaxy quenched in the heart of a searing cluster likely met its end through environmental violence, its gas stripped away by a brutal headwind. An isolated red nugget, by contrast, points to an internal drama, perhaps a ferocious burst of star formation that consumed all its fuel, or a prematurely overmassive black hole that heated its surroundings into stillness. The compact ones suggest a rapid, intense birth and a swift shutdown, while the more extended ones might hint at a slower, more protracted strangulation. This diversity forces us to abandon the search for a single, simple answer. Instead, we must see the young cosmos as a dynamic and often harsh place, where a galaxy's fate was shaped by a complex interplay of its internal constitution, its growth history, and the specific dangers of its environment. The red color we see is just the final, common outcome, the universal sign of a star-forming engine that has ceased to run. But the journey to that red silence, the story of how the lights went out, could be as unique as each galaxy itself. So we stand before a gallery of cosmic suspects, each with a compelling motive. The overmassive black hole, the violent merger, the searing cluster environment, and the galaxy's own furious youth all present a case for how the lights went out. To solve the mystery, we must weigh this evidence against the silent witnesses themselves, the red nuggets and their kin, asking which theory best fits their peculiar and ancient features. The case for a central, overmassive black hole is strengthened by the very compactness of these galaxies. A powerful outburst of AGN feedback would have been most effective at heating gas in the dense central regions where star formation would otherwise be rampant. It could have delivered a precise, surgical strike to the galaxy's heart, quenching it without necessarily blowing the entire structure apart, preserving that dense nugget of stars. The discovery of these proportionally huge black holes in some early red galaxies is a direct, physical clue that cannot be ignored. It suggests a sequence where the black hole grew first and fastest, becoming the dominant actor that then dictated the galaxy's quiet fate. Yet the merger, or Blitz quenching, theory also finds strong support in the shapes we see. Many of these early massive galaxies are not perfect spheres. They are often subtly elongated or show signs of disturbed structure in their deepest infrared portraits. These could be the lasting scars of that final, defining collision. A major merger provides a natural explanation for both the rapid consumption of gas in a starburst and the creation of a compact, puffed-up stellar core through the violent gravitational choreography of two galaxies combining. It is a single, dramatic event that writes a galaxy's entire life story in one explosive chapter. The environmental argument, however, struggles with the loners. We find early quenched galaxies drifting in the emptiness of cosmic voids, far from any cluster hot enough to strip their gas. This tells us that while a brutal cluster environment is certainly one way to quench a galaxy, it cannot be the universal explanation. The mechanism must also work in isolation. This fact elevates the importance of internal processes, whether from a black hole or a self-destructive starburst, as they can operate anywhere in the cosmos. This brings us to the quietest suspect of all, the galaxy's own internal structure and history. The profound compactness of a red nugget suggests its stars were formed in an incredibly dense, early burst. This aligns with the idea of a self-quenching initial generation of monstrous stars, or the early formation of a stabilizing central bulge that prevented further collapse. These are not stories of external catastrophe, but of internal destiny. A galaxy that forms its stars too efficiently, too early, simply has no future. It is a cosmic one-hit wonder. The most likely conclusion is not a verdict for one suspect, but an acknowledgement of a cosmic jury. Different galaxies in the early universe likely met their ends through different pathways. A dense red nugget floating alone might be the product of a ferocious internal starburst and a precocious black hole. A similarly massive but slightly more extended galaxy in a crowded proto-cluster was probably strangled and stripped by its searing surroundings. The universe, in its raw and creative youth, seems to have employed every tool at its disposal to build these giants and then silence them. The common red color we see is the final uniform state, the quiet after many different kinds of storms. This complexity, this lack of a single simple answer, is perhaps the most profound lesson. It reveals a young cosmos that was dynamic, violent, and diverse, capable of writing countless unique stories that all somehow led to the same silent end. The silent verdict of the ancient cosmos is now being challenged by a new witness. The James Webb Space Telescope, with its golden mirror gazing into the infrared depths of space and time, is not just confirming old suspicions, it is rewriting the timeline of cosmic quiet. Its unprecedented sensitivity is acting like a forensic scanner for the early universe, allowing astronomers to perform autopsies on galaxies that died in the cosmic dawn. Where Hubble saw hints and candidates, Webb sees with startling clarity. It is confirming the existence of those puzzling red and dead galaxies at redshifts we once thought impossible, solidifying the reality that quenching was not a rare event, but a common feature of a surprisingly mature young cosmos. But Webb's true power lies in going further back, to epochs even closer to the Big Bang. Already, it is discovering galaxies that appear to have quenched when the universe was barely 1 billion years old. This pushes the mystery into entirely new territory, forcing us to ask how any physical process could operate with such devastating efficiency, in such a negligible span of cosmic time. It is as if we found the ruins of a great civilization not in an ancient forest, but in a landscape that had only just cooled from its formation. The timeline for galaxy evolution is being compressed in ways that defy our previous models. Yet Webb offers more than just earlier snapshots of silence. Its powerful spectrographs can dissect the faint, redshifted light from these galaxies in exquisite detail. This is where the real detective work begins. By analyzing the precise chemical fingerprints and the ages of the stellar populations within these ancient relics, scientists can begin to diagnose the cause of death. Did the galaxy's stars form in a single, rapid burst, pointing to a violent merger or a self-quenching generation of titanic stars? Does the chemical makeup show an abundance of elements forged in supernova? Or is it more pristine, suggesting star formation was cut off before many generations could enrich the gas? The spectrum can even search for faint traces of activity from a central black hole long gone quiet. Each spectrum is a cosmic medical chart, revealing the symptoms that point to the specific ailment that halted creation. Webb is transforming this field from a collection of puzzling snapshots into a rich, detailed history book. It allows us to move from asking if galaxies quenched early, to understanding precisely how each one met its unique and silent fate. Galaxy by ancient galaxy. The universe, it seems, did not choose just one way to bring its earliest giants to silence. The emerging consensus among astronomers points not to a single cosmic executioner, but to a conspiracy of causes. Overmassive black holes, furious bursts of early star formation, and the searing violence of young galaxy clusters, all likely played their part in different galaxies at different times. This multifaceted explanation reflects the dynamic chaos of the young cosmos, a place where a galaxy's fate was the complex product of its internal character and the dangers of its environment. This mystery fundamentally reshapes our understanding of galactic mortality. We once thought of galaxies living long, steady lives, fading gently into a red old age. Now we know that for many of the most massive, death could come swiftly and early, a dramatic shutdown in the prime of cosmic youth. It reveals a universe capable of both breathtaking creation and sudden, decisive quiet. The story of these early quenched galaxies is still being written, with every new observation from telescopes like James Webb adding another sentence to their ancient history. To follow this cosmic detective story as it unfolds, keep your eyes on the sky and on the announcements from the world's great observatories. The next chapter in understanding why the lights went out is being revealed right now.